Hello everyone, my name is Earle. I'm a PhD student at the University of Glasgow with the Glasgow LISA group, and today I will be presenting the proposed design for an experimental backscatter measurement rig for the verification of LISA beam dumps and FIOS characterisation. So starting with the beam dumps. A beam dump in the context of optics can be described as an optical element that absorbs a beam of light. Beam dumps are required on the optical bench to dispose of unwanted light, making them a critical component for stray light control. Beam dumps will be required at multiple locations across the OB and need to be lightweight, compact, and space qualified. The current design simply relies upon multiple reflections between two highly reflective non-parallel glass plates. The highly reflective glass acts to dissipate the incident beam as it undergoes further and further reflections within the component. Not all of the light is absorbed by the beam dump. Some will be scattered, resulting in a level of back reflection. A conservative estimate of the current beam dump design predicts a back reflection to incident intensity ratio of the order of 10 to the 6. Whatever the design, the performance will need to be verified by experiment, and that is why we require a backscatter measurement rig. Onto the backscatter rig requirements. To start with, we require a beam that emulates the LISA parameters as much as possible in terms of laser wavelength, beam profile, beam size, and angle of incidence on the component. We want to direct this LISA-like beam at a component and measure the directly back-coupled light. A LISA beam dump might see tens of milliwatts incident power only to return tens of nanowatts down the incident beam path. So the backscatter measurement rig must be sensitive to very low light intensity. An intensity measurement is a relatively insensitive technique. It's much better to obtain a measurement of the amplitude of the weak light by using an interference technique in which the weak light field is mixed with a strong local oscillator beam. So the backscatter rig will use optical heterodyne interferometry. So I will now present the design concept of the backscatter measurement rig. We propose to use optical heterodyne detection in order to mix a weak frequency offset signal with a strong local coherent reference, resulting in an easily measurable heterodyne beat signal. In this scenario, the weak signal path is comprised of the returning light from the component under test, or otherwise the beam dumps. The light supplied to the weak signal and the local oscillator path originates from the same source and is immediately split by a fibre coupler. The signal path is then fed into a fibre circulator. This is a critical component that directs the input of port 1 to the output of port 2, whilst directing the input of port 2 to the output of port 3. Next, our signal path exits the circulator and passes through an AOM driven at 150 MHz. Our signal path is then launched out of a GRIN fibre collimator lens, where it propagates in free space onto an aligning mirror, through an adjustable strength neutral density filter holder, and finally onto a highly reflective piezo-driven mirror. The combination of ND filter and mirror is meant to simulate the beam dump, allowing for testing of selected reductions in returning intensity. The oscillation of the component under test is a key part of the design. It uniquely identifies the component in the frequency domain and shifts the frequency of detection away from 300 MHz. The light reflected from the mirror is directed back along the optical axis, coupled into the fibre collimator once again, and then once again frequency shifted by another 150 MHz. This weak signal path light is then mixed with the initially picked off local oscillator light via a second fibre coupler, and is ultimately detected by a photodiode and read out on a spectrum analyzer. And here you can see a bird's eye view of the current backscatter measurement rig experimental setup in its breadboard state. All the fibres and components are PM single mode. The fibre splitters are 50-50 ratio Thorlab splitters in the blue boxes. The majority of the components are from Thorlabs, with the exception of the AOM, Chikuch and Haugo. And the piezo mirror is contained within the silver tube within the purple box, and is normally oscillated at 3 kHz. So there are a few key points to note about this before I present the results. So some key points to note here. The light returned from the target has made 2 passes through a 150 MHz acousto-optic modulator, and the resulting detected heterodyne signal is therefore centered around 300 MHz. There are inevitable spurious back reflections internal to the AOM and to the post-AOM fiber interconnects. These contribute to a beat note at 300 MHz with upconverted noise from laser frequency noise and pathline fluctuations in the main and local oscillator fiber paths at nearby frequencies. We dither the longitudinal position of the target to provide a frequency domain separation of the signals from the spurious reflections and from the weak light that we wish to measure. A modulation frequency of 3 kHz and a dither amplitude of 3 wavelengths are currently used. By oscillating our component in this way, our signal is therefore a 3 kHz sideband of 300 MHz, and the signal amplitude is proportional to the amplitude of the light returned from the position modulated target and coupled back into the fiber. Additionally, switching from a laser diode to an Earle laser source yielded a 20 dB reduction in the noise floor. With the Earle laser source, we suspect coupling of environmental noise into the fibers is providing the dominant source of noise in the region of the 3 kHz offset from 300 MHz. Now to present the initial results from the backscatter measurement rig. The images you can see here are pictures taken of the spectrum analyzer display in 2 different scenarios. They are centered on the first sideband peak, 3 kHz above 300 MHz, and displayed over a span of 2 kHz. The image on the left corresponds to an instant power of 1 mW on the piezo mirror, resulting in a peak signal power of negative 37 dBm. This is the full reflection peak. The image on the right corresponds to the scenario where the beam is prevented from striking the modulating mirror at all. It shows a noise floor of about minus 137 dBm, with a small residual peak due to acoustic coupling from the piezo transducer into the nearby fibers. Comparing the full reflection peak to the noise floor, we achieved a measurement of a reduction in intensity of the order of 10 to the 5. I will now talk about the future work for the backscatter measurement rig. So, looking to the future, we hope to improve the performance and stability of the backscatter rig by progressing to a monolithic spliced version, where we have removed the fibre boundaries by splicing the components together. This will remove a lot of excess fibre in the system and reduce the number of opportunities for internal back reflections to occur. This will also make it easier to accommodate the fibre and the components in a more contained and insulated design. Then, hopefully we can aim this spliced backscatter rig at a real beam dump in order to measure its performance. And if that is successful, we can investigate the effects of beam dump surface contamination on its performance. This is important as contamination is expected to be the dominating scattering mechanism for stray light from the beam dumps. Next, we plan to improve the fibre collimator section so that we can better emulate the expected beam profile incident on the beam dumps. And lastly, the current setup only measures light returned that has the same polarization as the light directed at the target. There are some LISA OB applications where we may need to know the behaviour of the dump where the main return mechanism, scattering, might perturb the polarization state. Therefore, a new setup will be required for this, in which we explicitly form, using suitably polarized local oscillator beams, heterodyne signals for both back-coupled polarizations. Okay, and that's the end of my presentation. Thank you for watching.